Welcome to the rational roots theorem. Oh my gosh, so exciting. If we are investigating a polynomial, we need to figure out a lot of different things. A lot of times we need to figure out the degree, right? And if it's not a quadratic, you're like, oh my gosh, how do I figure out this cubic or this degree 9 polynomial? Well, there's a couple different ways you can do that. You can use Descartes' rule of signs, and you can figure out how many positive and negative roots there will be. But you can also use this rational roots theorem. All right, and this is what the rational roots theorem says. Here is the general form. So you know, in a textbook, you'll see this, right? This is just reducing each exponent by 1 each time until you get to the constant at the end in general form. It's just the general form. You've seen that. So what it really says is if, and I underline that 3 times because that's really important, if P over Q, simplified, so like in lowest terms, if P over Q, which I don't know what P is, and I don't know what Q is, could be like 3 halves, right? If 3 over 2 is a root of f, is a root. So if you plugged in P over Q in here, you'd get 0, right? If it's a root, if it's an x-intercept, then what it says is, then P, that top number, is a factor of a sub 0. That's the last term, okay? And Q is a factor of a sub n. That's the first term, or the first coefficient, right? So let's just read that again. If it's a root, doesn't say that it definitely is, but if it's a root, then P is a factor of this last one, Q is a factor of this last one. Well, how does that help us? Well, what that does is it helps us generate a list of numbers that could be roots. Because if there is a rational root of this polynomial, then it's going to be a part of this list that we're going to create. And that's really all that it is. It helps you generate a list. You could generate a list of all these different possibilities, and it might not be a root. But if there is a rational root, we know that it's going to be a part of those because of what this theorem says, right? So this is part of a bigger problem. Here's the in-between. So let's just look at an example. We've got 2x to the third power plus 3x squared plus 2x plus 3, okay? So what I'm going to try to do is, if there's a rational root of this, if there's a rational root, P over Q, I don't know what it is, then it's going to be, the top number, P, is going to be a factor of this number, and Q is going to be a factor of this number, all right? So let's just list all the factors of 3 over factors of 2, all right? That's all we're going to do. So let's go over this way. What are all the factors of 3? We're going to include positive and negative 1, right? Why are we including that? Well, because, and positive and negative 3, because positive 1 times positive 3, those are factors, but so is negative 1 and negative 3. Those are also factors of 3, right? Negative 1 times negative 3 is positive 3. Okay, so those are all my factors there. And then on the bottom side, we're going to have something similar, positive and negative 1. You're always going to have positive and negative 1, and positive and negative 2. All right, so now I need to look at all the different combinations because it's going to be a factor. It doesn't say what the factor is. So right up top here, if you're counting how many factors there are, you should be counting 4, plus or minus 1, plus or minus 3. That's 1, 2, 3, 4. And on the bottom, 1, 2, 3, 4. This is an easy example. You might have a really long list if there's a lot of factors of a number. I picked 2 prime numbers. Yes, 2 is prime. And I am looking at all the combinations. So let's just start off with positive 1. Positive 1 over top of positive 1, right? So I picked a positive 1 here, positive 1 there. That's one possibility. Then positive 1 on top, negative 1 on the bottom. That's another possibility. All right, I now could pick negative 1 on top and positive 1 on the bottom, but that would be the same thing as this, right? Negative 1 over positive 1, that's the same value, because if I simplify this, this is just 1. If I simplify this, this is negative 1, all right? Same thing going forward. If I picked negative 1 up top and negative 1 on the bottom, that would be the same as this. That would just simplify to 1. So I'm not going to write those down. Those I don't need to repeat them. But I do need to move on to this part. So now if I pick positive 1 up top and positive 2 on the bottom, that's good. That doesn't repeat. And what if I pick positive 1 on top and negative 2 on the bottom? That's great. But if I pick negative 1 up top and positive 2 on the bottom, that's going to be the same as this one. If I put negative 1 up top and negative 2 on the bottom, that's going to simplify to 1/2. So I don't need to put those repeats there. All right, I'm going to keep going now. I've exhausted all the possibilities with positive 1 and negative 1, really, on top. So then I go to 3. So now I pick 3 over 1, right? That hasn't been listed yet. 3 over, make sure I'm still in frame here, 3 over negative 1. Okay, that's another possibility. Again, if I put negative 3 up top and positive 1 on the bottom, that's going to repeat this one. Negative 3 up top, negative 1 on the bottom, that's going to repeat this one. All right, so I'm going to move on to the 2's now. So 3 over 2 and then 3 over negative 2. If I pick the negative 3 up top, it's going to start repeating these again. So I've got these are all my possibilities. I'm going to simplify them to make my list. 1, negative 1, 1/2, negative 1/2, 3, negative 3, 3/2, and negative 3/2. Here is my list. I've generated a list of possible roots. If there is a root of this polynomial, if it is a rational root, it's going to be in this list. But that doesn't mean that these are definitely going to be roots of this. It might be, or one of them might be a root of this, but it might not be. All right. So this works within the context of a bigger problem. If I just said, find all the roots of this polynomial, you would first look at the degree, say, oh, there's got to be 3 roots. Some of them might be real, some of them might be complex. Then you would look at the rule of signs. How many times does the sign change? Just looking at this f of x, I don't see any positive changes, right? You would generate this thing, this little table, and you'd figure out how many positive roots there would be, negative roots, so on and so forth. When you did that, you'd probably come up with more negative roots. I don't see any sign changes here. So if I did that, I'd generate something over here. So I would probably look at this list and say, I need to pick some of these negative roots. I would say, all right, I'm going to pick this one, negative 1, and I'd try to divide that by x plus 1 to figure out if it divides nicely and evenly, then it's going to be a factor, meaning that I would have a remainder of a quadratic, and I would slowly be able to reduce that. So this is in the context of a bigger problem. If you're listing all of the rational roots that could be a all the rational roots, this is your list. That's how you do it. Look at all the factors of the last number, look at all the factors of the first number, of the first coefficient, and write them all out, simplify it. That's what it says. Good luck.